Hello. Hello and welcome to this video where we read through the documentation of PostgreSQL. I have put the practical videos on hold for a bit. So the reason I understand that it is not very good for my YouTube channel to go to read through, as not many people are interested in read through, but I do it for the sake of completion, and I need to convince myself that I have not left anything out from the manual, because it's for me that I need to be convinced that the material covered is complete. So let's see how much we can go through JSON types. And in case you have not watched previous videos, then please go to my channel and watch videos from playlist in order. There is some basic practical information is there which you can read on. So JSON stands for JavaScript Object Notation. As you may know, you might be a web developer, then you would know JavaScript Object Notation. If you are a pure database person, then I would recommend that you go to this RFC and read about JSON if you don't know about JSON as well. The JSON data can also be stored as text, but JSON data types advantages that the values stored follow the JSON rules. Okay. There are also JSON specific functions and operators, which you will see in the next chapter. There are two different types. One is JSON, another is JSONB. For efficient querying, there is also JSON path is there, which we will cover. JSON and JSONB both accept almost identical set of values as input. The main difference is that JSON data type stores an exact copy of the input text, which processing function must be parsed on each execution, while JSONB data is stored in decomposed binary format, making it slightly slower to input due to added conversion overhead, but significantly faster to process. So no reparsing is needed. JSONB also supports indexing, which can be a significant advantage. Because JSON stores the exact copy, it will preserve semantically insignificant white space between tokens as well as order of keys within JSON objects. Also, if a JSON object within the value contains the same key more than once, all the key value pairs are kept. The processing functions consider the last value as the operative one. By contrast, JSONB does not preserve white space, does not preserve the order of object keys, and does not keep duplicate object keys. If duplicate keys are specified in the input, only the last value is kept. In general, most applications should prefer to store JSON data as JSONB unless there are quite specialized needs, such as legacy assumptions due to ordering of object keys. The RFC specifies that JSON should be in UTF-8. It is therefore not possible for the JSON types to conform rigidly to JSON specification unless the database encoding is UTF-8. You don't need to worry about that because by default the database encoding is UTF-8. Attempts to decode directly include characters that cannot be represented in the database encoding will fail. Conversely, characters that can be represented in the database encoding but not in UTF-8 will be allowed. The RFC permits the JSON string to contain Unicode escape sequences, which would be denoted like this, where X is a hexadecimal number. In the input function for JSON type, Unicode escapes are allowed regardless of database encoding and are checked for syntactic correctness. That is, 4x digits follow U. However, input function for JSONB is stricter. It disallows Unicode escape for characters that cannot be represented in the database encoding. The JSONB type also rejects \U quadruple zeros because that cannot be represented in PostgreSQL's text type. And it insists that any use of Unicode surrogate pairs to designate characters outside the Unicode basic multilingual plane must be correct. Valid Unicode escapes are converted to the equivalent single character for storage. This includes folding surrogate pairs into a single character. Then we have a note. Many of the JSON processing functions described in section 9.16 will convert Unicode escape to regular characters and will therefore throw the same types of errors just described even if their input is of type JSON, not JSONB. The fact that JSON input function does not make these checks may be considered a historical artifact, although it does allow for simple storage without processing of JSON Unicode step in a database encoding that does not support the represented characters. So when it converts the JSON to JSONB, the primitive types which are described in this RFC are mapped into native PostgreSQL types. Therefore, there are some additional constraints on what constitutes JSONB, and it does not apply to JSON. Corresponding to limits of on what can be represented by underlying data type. Okay. JSONB will reject numbers that are outside the range of PostgreSQL numeric data type, while JSON will not. Such implementation defined restrictions are permitted by the RFC. However, in practice, such problems are far more likely to occur in other implementations, as it is common to represent JSON's number private type as IEEE 754 double precision floating point number, which the RFC anticipates and allows for. When using JSON as an interchange format with such systems, the danger of losing numeric precision compared to data originally stored by PostgreSQL should be considered. Conversely, as noted in this table, there are some minor restrictions on the input format of JSON primitive types that does not apply to corresponding PostgreSQL type. So in JSON, if your type is string primitive type and Postgres is text, then Unicode is disallowed. If it's a number in JSON and numeric in PostgreSQL, then NaN and infinity are not allowed. Boolean to Boolean, only lowercase true and false spellings are accepted. Null and none SQL SQL is a different concept. So we have some example of expressions. So we select 5 as JSON. So these primitive values can be numbers, quoted strings, true, false, or null. So when we talk of quoted string, it should be double quoted. When we have array, we can have an array. You can pass it in a single quoted stuff surrounded by brackets, and then you have array elements. Then we have objects or dictionaries. We have key value pairs that we can select as JSON. The objects are surrounded with braces. Object and arrays can be nested freely. However you wish, you can nest them. When a JSON value is input, then printed without any additional processing. So suppose you take this input and the output is shown below. There is no processing done for this, for JSON type. But if you do JSONB, then you see that the order of keys are different. Okay? But JSON will preserve your order of keys. Another significant detail is that in JSONB, numbers are printed according to the behavior of numeric type. So for example, if you have this, JSON will print the scientific notation, but JSONB will not. Okay, it will give you trailing fractional zeros. That is this 0 it is talking about. Now, as I have said in past that or rather previous video, that you should actually never prefer the JSON type. We are covering this for the sake of completeness. And I've explained the reasoning with an example that why JSON type should not be used. In fact, I was supposed to talk about normalization, but I forgot about it and I did not prepare these slides. So we are not having normalization in this video. Another thing is that JSON data is subject to the same concurrency control consideration as any other data type when stored in a table. Although storing large documents is practicable, keep in mind that any update acquires a row lock on the whole row. Consider limiting JSON documents to a manageable size in order to decrease lock contention among updating transactions. Ideally, JSON documents should each be represented an atomic datum that business rules dictate cannot reasonably be further subdivided into smaller datums that could be modified independently. Now we have some JSONB in example. So we select foo from JSONB and then another foo here. So the scalar primitives values contain only the identical values. The array on the right side is contained within one on the left. Then here we have the order of array elements is not significant. So this is also true. Okay. I'm not sure what this operator will do. I think it is for equality, right? We are comparing it. So duplicate array elements also do not matter. The objects with a single pair on the right side is contained within the object on the left hand side. So this is contained within the left side. In fact, it would be best if I can show you that what is the output of this. Hang on, let me quickly see if my Postgres is a Podman PS message. No, I don't have the image. I don't want to create that. I will create an image and I will, in the next video, I will go through all these statements that what they do. Okay, so examples we'll go through. This is something I will note down and do that. The general principle is that contained object must match the containing object as to structure and data contents, possibly after discarding some non-matching array elements or object key value pairs from the containing object. I don't use JSON with PostgreSQL at all. I have never used it till now. So my knowledge of JSON and JSONB is quite limited. But remember that the order of our elements is not significant when doing a containment match, and duplicate array elements are effectively considered only once. As a special exception to the general principle that the structure must match, an array may contain a primitive value. So you see that here we have bar and here we have bar in an array. So it will give us false. JSONB also has an existence operator, which is a variation on the theme of containment. It tests whether a string given as a text value appears as an object key or array element at the top level of JSONB value. So here it will check whether bar is inside the array element or not. Here it will check whether foo is the JSON key or not. And here it will check whether object values are not considered. So this will be false. As with containment, existence must match at the top level. So if you look inside the JSON document further than level 1, then it will give you false. A string is considered to exist if it matches a primitive JSON string. So if it matches, it would be true. JSON objects are better suited than arrays for testing containment or existence when there are many keys or elements involved. Because unlike arrays, they are internally optimized for searching and do not need to be searched linearly. Now we have a tip here. Because JSON containment is nested, an appropriate query can pick explicit selection of sub-objects. As an example, suppose we have a doc column containing objects at the top level, with most objects containing tags fields that contain arrays of sub-objects. This query finds entries in the sub-objects containing both term colon pairs and term colon food appear, while ignoring any such keys outside the tags array. So we want to get the site name, but you see it will not match here and it will be false, I believe, or rather none. I would show all these execution and all these examples in the next video. We can accomplish the same thing with this. Okay, you can extract the tags. Okay, you can query on tags key as such by directly specifying this. But that approach is less flexible and often less efficient as well. On the other hand, the JSON existence operator is not nested. It will only look for specified keys or array element at the top level of JSON value. Now here it talks about the JSONB indexing. So the indexing of JSON documents is done through GIN indexes. Those are not B-tree indexes. And it can be used to efficiently search for key and key values pair. The GIN operator class is provided, offering different performance and flexibility trade-off. The default operator class will support queries with key exists operators question mark or question mark and. The containment operator at the rate, it was not a comparison, it is a containment operator. Okay. And the JSON path matches at the rate question mark and at the rate. So for semantics, we will have to go through table 9.1 for it. Let's go there actually. So let's see what JSONB operators are. So this operator actually checks whether the first JSON value contains the second. So whether this contains this. So it is contained, so it will be true. Then we have less than at the rate. So in this case, the first is contained in the second. So B2 is contained. Then we have question mark. Does the text string exist as a top level key or array element within the JSON value? So here the B exists as the top level. Here also B exists as an element. Then we have question mark. Pipe, do any of the strings in the text array exist as a top level keys or array elements? So B and D are given here. So B exists here, so it is true. Then we have question mark ampersand. Do all of the strings in the text array exist at top level keys or array elements? So A and B both exist. So possibly you can go through this. We will eventually go through this when we read chapter 9. So we're talking about the JSONB indexing. So the trick to create JSON index, not trick, the syntax is create index IDX gen and the index name on the table using gen, and the argument should be JDoc. The non-default gen operator class JSONB pathhouse does not support key exist operators, but it does support at the rate greater than, at the rate question mark, and at the rate. So the example would be you have to pass an extra argument JSONB path hops. So we have an example document here. So if this document is stored, we can query that select JDoc GUID JDoc name from API where JDoc contains company as magnaphone. So it will look for company key with value magnaphone, and if that is found, it will select the GUID and name. However, the index could not be used for queries like the following because the operator question mark is indexable. It is not applied directly to the indexed column JDoc. So okay, JDoc, I don't think it's an indexed column here. Okay. So we select JDoc. Give me a moment. Okay. Usually indexes are created on columns, but I don't see a column here. I will have to see what this JDoc means here. Okay. JSONB documents. Okay. This I will explain that what this JDoc is. Okay. Once the Postgres is up, we can see whether this JDoc is column or not. For example, in this one, there is no JDoc column, but we are still, JDoc may be the column name. Oh, I got it. So the JDoc is the column name in the table. I got confused, terribly confused. JDoc is the column name in the API table. Okay. So this is how we search. Now we're reading, however, the index could not be used for the index column. This we have also. Find documents in which the key tags contains key or array element QUI. So we have select the GUID name where JDoc column contains tags or V. It is a French word, I believe. V means yes. Still, the appropriate uses of expression index, the above query can use an index. If querying for particular items within tags column, tags key is common, define an index item. Index like this may be worthwhile. So in this case, we say JDoc arrow tags. So now you see that it is surrounded twice by parentheses. Now where clause JDoc tags question mark V will be recognized and an application of the indexable operator question mark to the index expression JDoc tags. So there is expression index. We will see, I doubt that we will read chapter 11. Now we will read chapter 11. We will cover. So now we can find the documents in which key tags contains array elements. Okay. A simple GIN index on the JDoc column can support this query, but note that such an index will store copies of every key and value in the JDoc column, whereas the expression index of the previous example store only data found under the tags key. While the simple index approach is far more flexible since it supports queries about any key, targeted expression indexes are likely to be smaller and faster to search than a simple index. GIN indexes also support @ question mark and @ operators, which perform JSON path matching example. So here we have a JSON path which is $.tags, and then we have bracket. So it looks for the tags where the array element is V. And similarly here we have the equality operator. Okay. For these operators, a GIN index extract process from the accessories chain. I'm not sure I understand this part. Okay. So I will not cover this paragraph. I don't know. I don't recommend. You can read through this. Also, JSON path hops operator class supports only queries with @ question mark, at operators. It has notable performance advantages over the default operator class JSONB ops. The JSONB path ops index is usually much smaller than a JSONB ops index over the same data, and the specificity of searches is better, particularly when queries contain keys and appear frequently in the data. Therefore, search operations typically perform better than with the default operator class. The technical difference between these two operator classes for GIN index is that former creates independent index terms for each key and value in the data, while the latter creates index items only for each value in the data. Basically, each JSONB path hops index item is a hash of the value and the key leading to it. For example, foo, bar, baz, a single index item would be created corresponding to all three of foo, bar, baz into the hash value. Thus, a containment query looking for this structure would result in extremely specific index search, but there is no way at all to find out whether foo appears as a key. On the other hand, a JSONB ops index would create three index items representing foo, bar, baz separately. Then to do the containment query, it would look for rows containing all three of these items. While GIN indexes can perform such an AND search fairly efficiently, it will still be less specific and slower than the equivalent JSONB path hop search, especially if there are a very large number of rows containing any single one of the three index items. The advantage is that it produces no index entries for JSON structure not containing any value, such as empty object for A. That is, the value for key A is empty. If a search for documents containing such a structure is requested, it will require a full index scan, which is quite slow. JSONB path hops is therefore ill-suited for applications that often perform such searches. JSONB also supports BT and hash indexes. They are usually useful if it is. So I have not talked about hash indexes. I have talked about BT indexes earlier when we were doing that. So we will study the indexes in chapter 11. So please wait for that, and you can mark this position in the video that I have not explained it yet. The BT ordering for JSONB datums is seldom of great interest, but for completeness it is. So in the ordering is object is greater than array, which is greater than boolean, numbering, string, and null. Object with n pairs is greater than object with n-1 pairs. Array with n elements is greater than array with n-1 elements. With the exception that top level entry level array is short less than null objects. Objects with equal keys of pairs are compared in the order key 1, value 1, key 2, value 2, and so on. Note that object keys are compared in their storage order, in particular since shorter keys are stored before longer keys. This can lead to results that might be unintuitive. So shorter keys are stored before longer keys. So in this case, we have AA1 key 1 greater than D1 D1, which should be true because it compares T1 value 1 and so that. Similarly, array with equal number of elements are compared in the order, that is element 1, element 2, and so on. So I think we will stop here, and in the next video I will finish the entire discussion of JSONB. So there are two things which remain. One is the examples of all this. In the next video I'll show you all the examples by creating JSON documents and everything. And the second is that I will try to find out information about this particular paragraph. Okay, or maybe we can revisit this, or we will find information in chapter 11. So that is something I'll remember. So I hope that you are enjoying this read through, and I'm sorry that my Postgres was not running. So in the next video I'll ensure that it is running. My OS changed recently and I forgot to create the Docker image again. So thanks a lot for watching the video. I hope you are enjoying and finding the videos useful. And if you find these boring, you may skip these videos, and possibly when we do the practical side of it, you can watch the videos again. So in the next video, we will see some examples of JSON types. It would be nice to query them and create tables out of those. So I'll see you in the next video with practicals on JSON. So till then, sayonara.